start the event, so I'll probably do the intros again. Sorry for that. So yeah, to repeat myself, so everyone, welcome to Memgraph Community Call. Today I have Vincent from Amboss Technologies with us. He's a senior data scientist there. And I met him on Twitter because I saw that he is doing a presentation about Memgraph on a blockchain conference. So I was like, oh, wow, this is cool. Vincent uses Memgraph for his research, for something cool he's doing. So I reached out and said, hi, Vincent, want to do the same for Memgraph community? I think it will be quite useful for them as well. And Vincent was glad to do that. So thank you, Vincent, so much for doing this and for sharing your knowledge with the community. And I'm looking forward to hearing more about the use case, how you use Memgraph, what do you like about Memgraph Lab, and to tell us a bit more about the use case you're working on and the Lightning Network, because like myself, I wasn't familiar with Lightning Network, and you providing that knowledge was really nice for me. So just a small information on the Livestorm. So as you can see, you can communicate in the chat for whatever you need. Use the questions tab to post questions for Vincent. So if you will have any questions about his presentation, just post there and I will read them afterwards out loud so Vincent can respond. And there will be 2 polls in the polls section. So if you find time, please answer them. And I think that's basically it from me. I hope that now more people join to listen in. So Vincent, you can share your presentation and start. And yeah, really looking forward to this.
All right, thank you so much for that warm introduction. Can everybody see this?
Yeah.
All right, great. All right, so as Katerina said before, my name is Vincent. I'm the Senior Data Scientist at Amboss Technologies. Thank you for coming to my talk today. It's titled Exploring the Lightning Network Using Memgraph. So just an overview of what we'll be talking about today. I'll be giving a quick intro to the Lightning Network, what it is and how it works. Then just why we decided to use Memgraph DB in our research on the Lightning Network, and then following that up with a personal project of mine called EllenStream, which allows you to load data from a snapshot of the Lightning Network into Memgraph, and then some interesting queries we can run from there. And then wrapping it up with some visualizations of this graph in Memgraph. So just to start with the Lightning Network is a layer 2 payment protocol built on top of the Bitcoin blockchain. For it to be a layer 2 payment protocol, the payments have to occur off-chain, and there has to be a trustless way to settle those payments on the base layer. Here you can see a snapshot of the Lightning Network from February 12th, 2019. In the paper cited below, and this is just a visualization that's significant to me because it's one of the first that I was exposed to while I was learning about graph analysis and the Lightning Network in general. And you know, from this you can see at a glance like which nodes are the influential nodes in the network based on their position closer to the center, then how much capacity they command in the network based on their size. And so just a lot of information packed into one small visual. So in order to really understand it, we should go through the life cycle of a channel. And in this example, we have 2 parties, Alice and Bob, and one or both parties needs to own and control some amount of Bitcoin in order to create a channel. So here, Alice owns and controls 4 Bitcoin, which she intends to place into a channel with Bob. So this process involves depositing these funds into a payment channel controlled by both parties. And the way this is done is by using a 2-of-2 multi-signature address. So it requires signatures from both parties to update or change anything about this channel now. Each party maintains a copy of the latest balance and can close the channel at any time. So this document you see under each party with the green check is the latest commitment transaction. They hold a copy of this and they wait to broadcast it to the blockchain, and that's what keeps the channel open. And until the channel's closed, they're able to update the balance. So updating the balance happens when both parties sign a new transaction, a new closing transaction, and then poison the old one. So you can see these two documents under Alice. The one with the X is the old, outdated commitment transaction, and the one with the green is the new transaction. So if she were to publish the old one, she would actually lose all the funds in the channel through what's called the Ellen penalty, and that's what keeps people honest in this network. And if they ever want to close the channel, they would just broadcast the latest commitment transaction. So when that happens, the funds are dispersed to either party according to that transaction. And until then, an unlimited number of payments can take place between Alice and Bob. So whereas before, on the base chain, each time you want to make a payment, that's one transaction. But here, you can consolidate an unlimited number of payments between Alice and Bob into just two transactions, one to open the channel and then one to close it. So this is one reason why the Lightning Network is a scalability solution to Bitcoin. It's no longer limited by this 10-minute block time or these mining fees per transaction. So moving on from there, if you're to extrapolate this idea of nodes and edges, you can create a network, but that would only really be useful if payments could occur between nodes. And so there's a mechanism for that, and it's called a hash time lock contract. And so these allow, in this example, Alice to send funds to Charlie via her connection with Bob and Bob's connection with Charlie. So these hash time lock contracts allow for atomic relay payments through intermediate nodes. And the way they work is Alice would deposit funds into a hash time lock contract, and you can see that here, where on either side there's a timer, and on the other side there's a lock. So the timer signifies expiration. So after a certain amount of time, this lock will expire and the funds would return to Alice. Whereas on the right side, there's a hash lock. And so if Bob is able to provide the preimage that this Bitcoin, the preimage to the hash that this Bitcoin is encumbered by, then he can unlock the Bitcoin onto his side. The trick is, though, that Bob doesn't know this preimage. However, he does know that that Charlie knows this preimage. And so by committing funds into a hash time lock contract towards Charlie, Charlie can unlock the funds on his side, thereby revealing the secret that Bob can use to then unlock the funds on his side with Alice. And so locking these funds into decrementing hash time lock contracts and then unlocking them in reverse order. And in that way, in effect, a payment has been sent from Alice to Charlie through Bob. So that's one more reason why it's a scalability solution for Bitcoin, because you don't need a direct channel with every peer in order to send them payments. But there are some caveats. Relaying payments requires liquidity. So in this scenario here, Alice owns and controls 3 Bitcoin towards Bob, but the reverse is not true. And so while Alice may be able to send payments through Bob to Charlie because there's liquidity allowing for that, the opposite direction is not possible. Charlie cannot send any payments through Bob to Alice because he doesn't own any funds on his side of the channel. And then one more on top of that is that the liquidity is not public knowledge. So you're only privy to the balance of funds in channels that you partially own. So Alice knows she owns and controls 3 Bitcoin with her channel to Bob, but she doesn't know who owns what in the channel between Bob and Charlie. She might know the capacity, how much Bitcoins exist in that channel, but she doesn't know who owns them. So this leads to a trial and error process when attempting to make payments in the network. Some more information here. So Bob probably wouldn't provide the service to Alice just out of the box. There is some risk involved. If there's an uncooperative node somewhere in the payment path, there's a chance for what's called a forced closure, which means that channel gets closed and you end up paying the mining fees for that. So to incentivize the behavior of relaying payments, there's forwarding policies so that you can get paid to route those payments by providing that liquidity. So part of that forwarding policy is the fee itself. So there's a scaling part to this fee that increases as the size of the payment increases, and then there's a base fee that is charged for a payment of any size. Then there's two more policies for the minimum and maximum amount that you're willing to forward along a channel, a Boolean flag to indicate whether a channel is disabled for routing, and then the lock time delta that describes how long those funds are locked up for in the hash time lock contract. So in this example below, if Bob were to charge a 1,000 part per million fee and a 1 sat base fee towards Charlie, then to relay 1 million sat payment from Alice to Charlie, Bob would receive 1,001,001 sats on his channel from Alice, and then send 1 million sats to Charlie, in effect earning that 1,001 sats in his fee policy. Then there's also some node attributes. So every node has a public key, and this is just the cryptographic ID of the node. Then they also have an alias, so that's the human readable name for a node. They have a color, which you wouldn't expect at first, but there's some nodes in the network that are related by color. For example, voltage, which is one of the largest node operators in the network. They help people join the network and run a node through their cloud service. Every single node has the same color, and so you can use that to identify clusters in the network, for example. Next up is features. So what kind of features the node supports. This is useful for determining like the version of a node, what kind of implementation they're running. It also indicates whether or not they allow something like large channels, so larger than a certain size. You have to have a feature flag for that. And then addresses. So how to contact this node, either through ClearNet or a Tor address, or in the case of Binance, one of the largest nodes, there is no connection info. Yeah, so at Amboss, we've been researching the Lightning Network. I joined sometime last June, and at the beginning, the process was something like loading a snapshot of the graph in JSON using Network X, and then running some queries, and then getting some results back. But after that script is run, you'd have to redo all of that work to get those same results back. So we really needed something like a database to keep this data persistent and accessible. And so we were looking at different graph databases, and for one of our initiatives, we wanted to do pathfinding, and in our benchmarks, we needed something with sub-second latency. So the current existing implementations for the Lightning Network can return responses for pathfinding queries in less than a second. So any graph database that can't do that is a non-starter, and we really can't compete against existing implementations. So in the end, we chose Memgraph because it's in memory, and for that reason, it's a lot faster. And then we just see it, we see ourselves using it more in the future for node operating decisions and some visualization. So EllenStream is a project I wrote, and what it is a control panel for loading graph snapshots into Memgraph. There's some code that exists in it that's since been commented out, but it can also stream graph updates from the Lightning Network into Memgraph so that you can have a real-time view of the network based off the network gossip. There's two parts to it. So the first part is a simple front end, and then a go back end that does most of the work, and then it comes with Memgraph included in the Docker file. So almost everything is set up from the get-go. So here's a link to that project. I'll give everybody a couple seconds to scan the QR code if they'd like, and then the link to it is here as well. And while I'm waiting for that, I just wanted to mention we currently have an ad out at Bitcoiner Jobs for a machine learning intern. We're still interviewing for that position, so if you or you know somebody who's interested in it, please apply. So yeah, I just wanted to throw that out there while people might be scanning this QR. Give it a couple seconds. And so that's pretty much the presentation. We'll be going off of that and setting up the project, and then running some queries in Memgraph. So if you follow that link, it would take you to this page. Don't bother using this link. It has this port number in it that breaks things. So just use the URL up here. It would open up a terminal. I already had it set up from practicing this morning, but we'll take it from the top. So git clone that link, and so it's copying the project along with the snapshot, which is probably the largest part to it. Change into that directory and let's just see what's here. So hopefully everybody can see that. So there's the Docker file for the project itself, a collection of some queries that we'll be using, the graph snapshot, the compose file for orchestrating all of the different parts of this project, and then the Go code itself. So in order to start it, just Docker compose up. It'll have to download the images for you, so that part might take a little bit longer on your own computer, but we can see we have something running at port 8080 and then port 3000. So at 8080 we have this graph control panel, and then at 3000 we have Memgraph. And it'll see that you're running the database locally, so it'll just have it set up for you. So yeah, just connect to it. And then loading that local snapshot, so what it's going to do is drop that database, add the indexes, and then add the nodes and relationships again. And then run a couple of setup queries for fixing denominations in the channel policies and a few like network metrics like between the centrality. So that'll just take a couple seconds, but it's already halfway done. And here's that job I was mentioning earlier. So machine learning intern at Amboss Technologies, bigcornerjobs.com. It looks like it's done. So you wouldn't have this right away. I think you would see something like this. So you'd go to collections. This should be empty. It'll look like this. Give it a name. So we'll call this demo. And then import queries. And so it should open up to the project folder under EllenStream. Use this latest one, Memgraph demo. So here we have 13 queries just for running the running against this database to learn more about the network. First one's not spectacularly interesting. There's just an idea that there's 0 degree nodes in this network. So the reason why a node with 0 degrees might exist is because they either have all private channels where they have open channels and they're participating in the network, but they haven't announced them, so nobody except the other party knows that they exist. Or this node has had channels at some point in the network, has closed them all, and still has remained online. So in either case, not particularly interesting to us, but what is interesting is the number. So there's about 3,500 such nodes that are either all private or still online but with no channels. Next up we have node capacity. So this just takes the incident capacity of a node, takes the total, and then sorts them so that we get an idea of which nodes in the network are the largest nodes. So you have the alias here, which is the human readable name, the capacity denominated in Bitcoin, and then the capacity denominated in US dollars. So async, the largest node in the network, has 464 Bitcoin in capacity, and that's about $30 million. OKX, which is an exchange, similar story, 436, and then 28 million. Another exchange, Bitfinex, 25 million, Binance, 20 million, Kraken, 17. So just very, a large amount of money locked into these channels with these exchanges. And then the next three are all routing nodes, so routing payments another exchange, a mining company, another exchange, but for Nostra assets. So yeah, I mean, there are some large entities using this network, and it's good to know, who they are. The next up is Wombo node. So Wombo is terminology taken from SpongeBob, but the idea is there's a specific capacity of channel. Beyond that is considered a Wombo channel. So in order to accept channels of that size, you have to explicitly say that you will in a feature flag, feature number 19. So what's interesting there, though, is if we consider nodes that are either all Wombo or all non-Wombo. So in this first query, these are all nodes that only accept channels greater than 16 million. And so Binance, it is an exchange, they only accept channels of at least 25 million, so a quarter of a Bitcoin or greater, which is interesting. But the other side of it is channels that have a large capacity, but they have small channels. So CoinGate, which is another exchange, doesn't have any channels that are greater than 16 million. And you would think with an exchange, there wouldn't be a limit to the size of payments they're willing to accept and trade for a different currency. And yet there is. So you can see that there exists at least one exchange that's bottleneck is channel capacity. So next up is between the centrality. So looking at between the centrality, which is the ratio of shortest paths that a node lies on relative to all shortest paths in the network. And here higher is better. But what you can see immediately is nodes like Async, which I mentioned before, has $30 million in capacity. They also have a high between the centrality. So if you were to take any random pair of nodes in the network, there's a 9% chance that the shortest path between them passes through this node. And so is the case for these other exchanges: CoinGate, Wall of Satoshi, Kraken, NiceHash, Liquid. They all have high between the centrality. They're very central to the network. And that just helps you know who's important in the network when it comes to pathfinding. So next up is fee ratio. So this idea is useful for determining like the syncness or sourceness of a node. So if I go to our website, Amboss Space, and I look at which nodes have had the greatest capacity increase in the last 24 hours, C equals is one of them. And in their fee report, we can look at their outgoing fee, their average outgoing fee versus their average incoming fee. And so this gives us this fee ratio here gives us an idea of how much more it costs to for this node to receive than it does for it to send. So this node charges 2.6 times what it costs to receive than it does to send, which means it's probably a source in the network rather than a sink. If you think of a sink in the network, they would want it to be cheap to receive, and they would end up receiving more. So by identifying these nodes in the network, then we can use a heuristic to determine like where funds originate in the network and where they usually detonate. So yeah, I mean, just looking at this, so this first one just sets them all to 0, but then the next two get their incoming and outgoing, and then the very last one sets the fee ratio, and it should be descending. I'm not sure why it's not. Oh, because it's ordered by total capacity. So yeah, we're looking at these influential nodes and then their fee ratio. Async has a fee ratio of 0, so it looks like a sync. Most anything with less than 1 is probably a sync. But if you look at Wallet of Satoshi has 2.4 as their fee ratio, so they're most likely a source of funds in the network. So yeah, I mean, we're using this kind of information to determine payment origins and destinations. The idea would be a routing node would want to place themselves between those. I think this one has the results a little bit more organized. But yeah, if we wanted to look at the biggest sinks, Async, Binance, Kraken, NiceHash. The biggest sources, Wallet of Satoshi, Cyberdyne, EllenBig, which is a routing node, Y'alls, AllNice, Africa Free Routing, the Bitcoin company, which the Bitcoin company and Azteco both sell like Bitcoin vouchers or Bitcoin gift cards. Next up, so looking at the subgraph of the top 100 nodes by betweenness. Actually, this one. Then you can see through this visualization which nodes are the most influential, at least by size. So out of these 100 nodes, there's only really a handful that have a large amount of capacity. So they really just dominate the rest of the network in terms of like redundant connections and their positioning. But if we try a different style, so this current style is based on total capacity, but if we instead base their size off of their betweenness centrality, those same nodes that I pulled out, some of them have high total capacity, but they have a really small betweenness centrality. Whereas there's some that have a small capacity, but a really high betweenness centrality. So that might tell you that this node, for example, or maybe this node, these are nodes that are provisioning their capacity in a way that increases their betweenness centrality. And that might indicate that they're intelligently operating the network and might provide routing opportunities for you, for example. So yeah, I mean, that kind of analysis is important on our side. And the next, I mean, this is the free network. So these are all channels in the network which don't charge any Bitcoin to route payments. This first one is where it's free in at least one direction. And the next one will be where it's free in both directions. But you can see there's a pretty sizable subgraph of nodes that are willing to route payments for free. And this next one is much smaller, but this is where it's free in both directions, which kind of highlights some special business relationships between nodes in this network. So Africa Free Routing obviously allows for free routing. Then if you look at this cluster of larger nodes, what you'll find out is that they're all owned by the same person. So EllenBig, EllenBig, EllenBig. And of course, if they're owned by the same person, they're not going to charge themselves to route their own money. And yeah, so I mean, just looking at these relationships, you can get an idea of nodes, well, at least in this visualization, which nodes have a high betweenness and also have free routing. So yeah, making decisions based on that. So that's the free network. And then these next are just related to pathfinding in general. So if we picked two nodes in the network, we limited the max fee that one would pay to pay the other, and then give it a payment size. So showing us all possible. Showing us all possible payment paths between those two nodes. I think what happened there was I had a section highlighted when I said run, so I just ran that. But anyway, so they're color-coded to show the origin and destination. So this is the origin, this is the destination, and then this would be all paths, all payment paths that exist between them below a certain fee. And from here you can get a glimpse of like, well, this node only has 2 outgoing connections that it can really use. but one of them is a lot more useful than the other, right? And if you were going to start your payment finding process, you might start by only considering payment paths through this node, for example. But just this picture in general gives you an idea of the connectedness of these two nodes and how easily a payment might occur between them. This next one, so this is all payment paths color coded. So this is starting with a node at the center and then branching out from that one. Let me change the pub key just for a second. And if all goes well, we should have, yeah, okay. Okay, yeah, I think this one, the style doesn't work, so give me just a second. To use Memgraph Lab from my desktop. If it loads, because it should have the styles correct. Bear with me here. Yeah. All right. So from here, you can see color-coded is the source of payments, and then the rest of this network is are the nodes that this node could pay under a certain fee. So, and then color-coded here, like the brightness of the gray is how close they are. So you can see there's only a handful that are about one hop away, it's like 3 nodes, and then several nodes that are 2 hops away, and then as you increase the number of hops, you're going to have more that you could pay, but this is just showing you those shortest paths from this node as the origin to all of these nodes as the destination. And so you can see with a payment size of 100,000 and a max cost of 100, so a 1% fee on the Lightning Network, this node can pay 5,000 nodes, which is a little less than half, and that's just through 2 of its connections. So yeah, I mean that's just the idea I'm trying to get across, is that this network allows cheap payments to most of the greater network.
So that was a great presentation, Vincent. Thank you so much. I really enjoyed hearing about it. So to start off with questions. So if anyone has any question, feel free to post it in the questions tab. I have my own, of course. To start off, like, I think everyone noticed that the visualizations are awesome. I mean, I think, did you put a lot of work into that, or like, was it hard for you to do that? And can you share with the community, like, your experiences and studies in Graph and Lab?
Sure. There was a lot of like great example code on the different Memgraph tutorials. So especially for like the sizing, there's some code out there that does all the normalization for you. So that was a lot of help. But then it was kind of up to me on how to use it. So, I mean, one way, the obvious way was total capacity. Then there's betweenness, but then you could also like use the fee ratio, which I hinted at a little bit. And yeah, I mean, it's just a fun process to explore the graph and being able to export those queries, so like I can save them and I can drop the entire database and not worry. So yeah, it just helped with iteration.
Yeah, and it looks so cool because even if you're showing this to someone who doesn't understand that much Cypher or anything else, you can still kind of get the insights from the data,
Yeah,
from the visualizations. Yeah,
and
that's really
that's
cool.
it was really helpful for like, yeah, just showing how well connected any pair of nodes are. And you know, when we're speaking to our clients, like they have certain business relationships with other nodes in the network, and they just really don't know where they stand in terms of connectedness. And so, yeah, I mean,
Mhm.
having those visualizations helps us determine like where the weak and strong points are.
And regarding Memgraph, I saw you used a lot of all shortest stats and so on. So which feature is the most valuable for your project? Which kind of queries were you running the most? I mean, we saw some of them, but what is
Yeah.
your point of view?
So I didn't want to dive too hard into like the constraints on pathfinding, but like there's silly things. So um, in that example between Alice and Bob, Alice pays the fee on the channel that she has with Bob, but the fee that she's paying is according to the policy of the channel in front of it. Does that make sense?
Yeah.
So like that nuance makes all the difference when you want to get like an accurate cost for a path. You have to do the math correctly. It's all source routed, but you have to work backwards from the destination. So like there's all these little quirks to the pathfinding that things like the lambda expressions and conditional expansion in Memgraph really simplified.
Mhm.
Uh, so yeah, I mean, just um, yeah, being able to use those expressions to accurately keep track of how much a path costs without having to write a whole custom module.
Yeah, that's true. That's true. Like the expressivity of that cipher query is a nice thing to have.
Yeah.
And do you like have an advice for someone who is just starting to use Memgraph? So I see you've used Lab, you use quite a lot of Memgraph features. Do you have an advice for someone who is just starting and don't know where to start, how to start?
I would say like developing that EllenStream project of mine. I mean, it's just two buttons, right? But when you find yourself like making the same queries over and over, or doing like the same process where all these steps have to be done in order, like you make a button for it. Um, and it helped me out a lot more to just,
Hmm.
you know, if I need to reset the graph and have it exactly like I need it, you know, you can make these kind of tools and you can make a small API to do it all for you.
Do you know now, will the project be available publicly later or?
Um, I think I'll keep it up for a little while. Yeah,
Yeah,
I usually just take it off, you know, a couple weeks after if things start changing.
yeah. So everyone, yeah, I sent in the chat the link to the project so you can take a look while it's up to see what Vincent created. And maybe to wrap it up, Vincent, can you tell me like what is the future of the project? Like what are you working on now and what's next?
Sure. So I mentioned some benchmarks. We recently came out with research on predicting the balances of channels based on the channel policies and other public information. And so we have some models and they seem to be useful. We're running benchmarks to evaluate just how useful and then just using those results to slowly iterate and improve. But yeah, so mostly focusing on pathfinding, but like I said, we're also looking for machine learning in turn for like simulation-based tasks. We're trying to use research involving MaxFlow to see like to come up with some network level SLAs. So like there's some research out there that's been really great, and we'd like to iterate on it, and we need some more hands on deck, you know.
Yeah, so anyone who wants apply for the internship position, I think it should be great, and I'm looking forward to hearing your progress on the research and the results. Thank you so much, Vincent, for joining this community call and for sharing your story with the community. Anyone, if you have questions for Vincent, you can post them in Discord. I will forward them, or Vincent will see them. And thanks everyone for joining. And that's it. See you soon on the next community call, and enjoy the rest of your day.
Thank you so much.
Thank you and bye.